it means you need to participate. So I've got 20 minutes of speaking time. Maybe you're going to do this, sorry. Okay.
You got it.
I've got 20 minutes of speaking time, and the other 20 minutes are for interaction time. So you've got to ask me questions. And I guess the time I spend answering your questions comes out of the audience time, and then...
Yeah, exactly. So like, if you ask a question, we're not just recording timing your question, we're timing also the answer to the question. So when he gets back into the rhythm of his talk, then we switch it back to audience, or to speaker time from audience time. And then the goal is, since we have another chess timer in the other room, so we don't have the projection right now, but Luke will helpfully stand here with this. So I hope you can see it. Can you see it? Yeah. Okay. So, it's here.
So are you ready? Are you ready to interact? I hope so. Okay, great, excellent.
And when Stephen looks over at you, just show it to him. Here, I got it. All right, so start.
Okay, great. So, hi everyone. This is my provocatively titled talk, Dragging Unix into the 1980s. That's what, if I'm feeling facetious and people ask me what I'm working on in my research, that's what I tell them. So hopefully I'll be able to explain it to you if my page down button starts working. There we go. Okay, so once upon a time in the 1970s, there were these guys, Ken Thompson, Dennis Ritchie. They created Unix. Unix has gone on to basically be the foundation of all our mainstream operating systems today. I consider Windows or Mac OS, they're basically Unix-like operating systems. They're 1970s designs, and we sort of build stuff on top of that, right? So we like to imagine, like any technologist or person who works creating something new, we imagine that we're working slowly towards this wonderful, fabulous future. This is concept art from Disney's Tomorrowland film, in case you're wondering. Tomorrowland, that's where we're going. Okay, that's technology. But this is my picture of what we've actually got. So it's just, these Unix guys, that's supposed to be a representation of the god Orion. Was Orion a god? Anyway, and then we build a load of stuff on top, and the whole thing is very ungainly. It's sort of standing on the shoulders of giants, but we sort of layer things up, and we never actually get rid of this Unix guy. Even though we always aspire to throw old software away, right? We're always saying, oh yeah, this old stuff is just legacy and it will go away and our shiny new thing will take over the world, and we've just used this Unixy C stuff, whatever it is, as a sort of foundation, as an immutable building block to build stuff on top of. But that isn't what actually happens, right? The Unix guys are hanging around, the 1970s stuff is still there, it's underneath. We could do a sort of archaeological dig, we could drill a core through our software and we say, oh yeah, we've got down to the 1970s again. Another way of putting it is we're losing at Tetris, right? Stuff is building up, but it's not sort of going away, so it's sort of everything is getting horribly out of control. So my take on this is that we should actually be thinking about doing less layering and doing more evolving in some sense, which I'll try and explain to you. So a cool thing about software is that software is built with other software and it runs on other software. And so we can actually change the qualities of our software by sort of inventing a new material. So we don't have to rewrite all our software to give new qualities to the existing software. We just need to rewrite the infrastructure, so things like the compilers and the operating system. We need to enhance those. We can actually make shiny new things out of old things, right? We don't need to rewrite the world from scratch. So a lot of my work is about doing that. It's about saying what is the material is sort of my metaphor, saying how can we make a better material out of which all our existing software can be realized without sort of rewriting everything, rebuilding everything from a new world. So one of the places I get a lot of sort of influence, a lot of my inspiration is from Smalltalk. This is a sort of 1980s or 90s style picture of a Smalltalk system. It happens to be Squeak. And one of the interesting things we can do here is that you can see it's showing us a view of our program as it's running. So it's got this sort of browser thing, and it's telling us that our program contains these different classes, like we've got, collections of something, and then we've got some sort of method saying is empty, and it's showing us the code of that method and just letting us edit it from within. So we get this really fast feedback cycle. And so far that sort of facility has been realized in systems that are layered above Unix, right? But we've never managed to realize it in the core. It's not in a very convincing way. So how am I doing for time, by the way? Okay, so I'll talk for 1.5 more minutes, and then I'm going to open it up somehow. So I've got this core project called liballox, and it's basically a runtime library plus some extension to the tool chain, so it interferes a little bit with how you compile and link stuff. And it builds in a sort of slightly more sophisticated notion of memory into your existing programs, right? So it got this notion of type, so memory in Unix doesn't really have a type, it's just kind of bytes. But in liballox, you actually do have type information in your program, and also has a notion of allocation that you can think of as a generalization of memory mapping. And this is these are concepts that were there, they were sort of latent there already in our programs, in how we build software. It's just sort of drawn them out. I'm sorry about the stray sentence at the bottom, I meant to delete that. A foundation for things, for important, interesting, exciting things. So here's a little picture of how that works. We already, in a modern Unix, we have some kind of introspection ability, right? So we can ask the operating system, this is Linux, we can ask it using this proc interface, say, what are the memory mappings in my process, right? So here, this is a cat process introspecting on itself, and it says, well, you know, I've got, the first few lines are like saying, I've got the executable, that's why they say at the end, bin cat. They're mappings of the executable, and then we've got a heap area, we've got a memory map file that's something to do with locales. We've got a couple of other binaries in the mix, we've got a libc and an LD, that's our dynamic linker, which I should get onto later if you ask me the right questions. We've got a stack, we've got some stuff to do with the kernel. So we can sort of get a view of some amount of structure of what's inside our process. And I've just sort of drawn colors on these to sort of group them. Some of these are kind of related, like the first two are basically the text segment of my cat executable, and the next one's the data segment, and then some other things. So there's a bit more sort of grouping we can do, and we can start to think of the structure of our address space as actually kind of like a tree. So we've got this first layer of stuff, which is these sort of segments, or maybe mapped files, or sort of coarse-grained chunks of stuff. And then we've also got things like a heap arena, that's also a kind of top-level thing. But underneath that, we've got the chunks. So maybe our heap arena is being managed by a malloc implementation, it's being parceled out into chunks. And then maybe underneath that, we've got more allocators, right? We might have an allocator that works by getting a big chunk of memory from malloc, and then parceling that out to its clients, and so on. And then at the very bottom of this tree, we've got individual chunks that are sort of meaningful to the programmer, so individual variables or maybe sort of fields inside a struct, inside a heap chunk, and so on. So we've got the structure, and what liballoc is doing is we're just making that structure visible and available, a thing that we can build on. So that's like one example of evolving Unix. So type information is something that lives more sort of further down the tree. We don't really have types of the sort of top level sort of memory mapping, because it's better seen as just opaque bytes, but we can say, well, subdivisions of that, we can attach types to it, say this variable is an int, or this malloc chunk contains a particular record type, struct type, something like that. So we can hang our types off the lower levels of the tree, and if you're interested, then there's some sort of type descriptors that the liballoc tools will generate for you, so that these are sort of literally records inside your program when it's running. So this is my little silly example. I've gone on a bit too long, sorry. A silly example of a data type called ellipse, and we've got basically a reified notion of what it is, a runtime. This is just describing the containment structure. So saying inside an ellipse, we've got a double at offset 0, and another double at offset 8, and then a point at offset 16, and that point is itself consisting of doubles, and there's other things in there, like functions, pointers, enumerations, and so on. So it's about time for you to start interacting, but are you wondering why this is useful? Why this is possible? I once gave a talk about this, and I found out later that some people in the room didn't believe it was possible. No? Okay. Yes. Question.
Why?
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 Why do it?
Yeah.
Okay. Well, luckily I can come on to that. So slightly, I don't know. So just to answer your question, there's a lot of things we can currently do with this. So, for example, people say, oh, a Unix process environment is very unsafe, right? Because memory is just bytes, and what do those bytes mean? And the system doesn't have any understanding of that, so we can't do things like dynamic checking in a meaningful way. Or people think of the C language. It's wrong, actually, to think of C language as just working over raw memory. It definitely doesn't, especially modern C. But people have this mental model of process without any sort of meaning or structure, and the program is just kind of blindly doing stuff to bytes. Once you have this model of memory, you can start doing all sorts of things. You can do runtime checking, that you're actually doing the right things with your pointers. You can do dynamic inspection at debug time, so you can say, well, your debugger just says, I've got a void pointer. So I can actually say, well, what is the thing on the end of that pointer? Please tell me. So I use that, now that I have that at runtime, I use it all the time when I'm debugging sort of low-level code. So those are two things we can do with it. Any more questions? Yes, Ed.
You should speak into the microphone right behind this.
Sorry, I'll start again. So this all sounds very useful to an attacker who may wish to know where some libc function is existing but doesn't otherwise know because of ASLR. And now we have introspection to tell them where it is.
Yeah, you're absolutely right. So my high-level take is that we can make C code memory safe, and so that mitigates that pretty well. I have another talk about that if you're interested, but I can't give that talk right now. But you can sort of see how, if I know what's in my memory, I can use that for good as well as evil, right? And I can instrument my code so that it can actually check that I'm staying in bounds. So there's a lot of assumptions about the threat model that this changes, and it's a huge question, and I'm not saying I know definitely that this is perfectly secure, but I think it's there are pros and cons here, so I'm not super concerned about it right now. Any more? We're going to be back on my time in a minute. Yeah, oh, one more question, yes.
I see lots of references to files in your slides.
Yeah.
And I mean, who does files anymore? It's all kind of, buckets and HTTP requests.
Ooh,
and
I do
if we're really thinking future, do we get rid of the files?
I like files. Well, so one of the things I've realized recently is that, this is in danger of getting political, but basically, the agenda for what, new technology is or should be is set by, huge organizations and the needs of huge organizations running huge data centers. I quite like the idea that I write programs, or I wrote the sort of small-scale industries. Like I'm still really old school. I had a lot of trouble with setting up because I needed VGA, for example. Anyway, I like running simple things that I understand, and I like my calendar as a text file. And I like the fact that it's within my means to have simple programs that working with relatively simple data. That's probably a tangent. That's not the best answer to your question. I mean, I think we use files. Who uses files here? Yes, everyone uses files. Okay, I didn't need to go on my rant about political stuff in the end. Anyway, okay. Any more before I go back to me time? Granddads. Yeah, no, it's fine. I take that. I'm not a granddad, but I could be. Okay. Right. I'll keep talking for a little bit. Where did I get to? So.
Sorry.
Oh yeah, Dylan. Yeah.
Can you go back one slide, please?
Yeah, that means forward, actually.
Oh.
That one, yeah. Is that the one?
Oh, sorry, one
Next
more forward.
No. Sorry, I got the wrong way.
Anyway, there was something about interacting without FFI.
Yeah.
That was...
So that's a whole other talk. Luckily, you can see that one on YouTube. Okay. But you can also talk to Guillaume. So I have a very good intern at the moment back in Kent who is working on... I'm pressing page up when I should be pressing page down. That's what's going the wrong way. Who is working on an extension to CPython that is basically saying, we don't need FFIs when we have this data. It's not that simple, but the fact that native stuff is exposed in this relatively rich way, so you can just have your Python interpreter kind of figure out how to interact with that in a much more direct way than previously. Yeah, have I answered your question?
Yep, I'll come visit this Kent place sometime.
Okay. Right, so back on me time now. Good. Okay, so one of the things you get as part of this liballox system is that you get this sort of meta-level API. So as we saw in the sort of tree picture, if I get back to the tree picture very briefly, there's basically a whole bunch of different bits of, a whole bunch of different allocators that are responsible for managing different bits of memory here. So one sort of allocator is the bit of basically the stack allocator that's in your kernel. So you kind of overrun your stack and the mapping gets extended up to a certain point, things like that. And we have malloc in our picture here. We also have the dynamic linker that created all these segments, right? We talk about static storage, but actually on a modern Unix environment, there's no such thing. It's pretty much all dynamically created, even sort of the binaries that we've loaded, right? It's all dynamic. So we can think of the dynamic linker as an allocator as well. So allocator is one of those abstractions that it's not obvious to begin with, but when you have it, you sort of think, oh, yeah, that's an allocator too, and so is that, and it becomes really useful. So this meta-level API, this is massively simplified, but it's just a rough picture of, you can ask questions about arbitrary pointers in your program, and they basically get dispatched to whatever allocator is managing that particular piece of memory, and you can ask questions like, what is the type of that memory, where was it allocated, what are its bounds, so on. Okay, so that's a high-level, sort of meta-level API. I could give you a quick demo. Do I have time for that? Are people keen for a demo? I'll give a quick demo. Okay, yes. So, yeah, you asked me to give a demo. So this is all built with. I've been trying to get modern. Sorry, is that a question? Yeah, I will do. Don't worry. I've even made a shell script specially for doing that. Is that big enough? Can you see? Oh, you've got even more screen than I have. Yeah, excuse me, I knew that. Okay, so I have been modernizing a little bit, and I have been using Docker, basically because liballox has a lot of dependencies. Oh bugger! Anyone know what that means? And then that big thing, right? Okay. Oh, wait a sec. It's on my other desktop. I still had it open because I was practicing. I'm going to kill it. Okay. Oh, it's already dead. Okay, great. Go on, please work. Yeah, okay. So this is a really simple program. If you download liballox and then you read the README, I'm going to have to do that because I can't remember what's in the README. Basically, the README will tell you how to build this container, and then I'm going to... Is that enough? I think I need about 28 lines here. Okay, so the README, and it will basically do the build for you, and except I just changed some stuff, so I need to change that. Keep changing things. And this is just a really simple C program, and all it does is takes a few pointers that happen to be available in the program, and it runs liballox, it runs the relevant calls to tell you a bit about them. So if we, whoops, E off, there we go. .c, it's there. Okay, so I should be able to run alloc.cc. Alloc.cc is just a wrapper around your normal system compiler. It just interferes a little bit with compile time. It does a little bit of source level analysis. It interferes a little bit with link time, but it's basically just you're running your C compiler with a few extra commands thrown in. Some of those commands are going to generate that metadata that I was showing you earlier. Include the include directory. test.c. Okay, so is this going to work? It's probably going to complain about one or two things. Variable size local. That's fine. It's going to terminate. Yeah, it's terminated. Okay, great. And then we can run it. We actually, the way I take over user space is using this horrible LD preload thing, but it's kind of an irrelevant detail. But if we get time, I'll tell you how to do it better in a second. So we can run the test program. I should have disabled this debug printout, but basically I'm going to show you the test.c again. So what it does is it has these pointers here. It's just saying, well, I'm going to iterate through this list of stuff, and we're going to ask liballox what it can tell us about these things. So we've got main, we've got p, which is our local. Excuse me, p is a pointer to some heap memory. So it's going to tell us what is in that heap memory. We also ask it about the pointer itself, so the local variable, and also argv. Argv is kind of interesting because it doesn't come from any C code, right? It comes from outside. The program. So if we run it, in fact, I've already run it, haven't I? I should have disabled that. But basically, the lines beginning with at are the ones you'll be looking at. So it knows something about, what is main. Main is a function. It doesn't know the size of main. That's a bit weird. Should probably fix that bug. But it knows that it's a function from some argument types or some other types. We know that our malloc chunk, the thing that we allocate with malloc, is a thing that's an array of ints. It hasn't filled in how big the array is. It actually does know that, but that's it does it kind of lazily, and this code hasn't poked it the right way yet. We know that we have a stack frame, and the local p that we had, the local variable p, is inside that stack frame. So stack frames become kind of like a struct type, sort of. The stack frame for a particular window of program addresses is a particular struct type. And then we've got also this auxv. So it knows that there's this thing on the stack, the initial stack, the auxiliary vector. That's just basically a blob of stuff that the operating system gives us at startup, and liballox knows about that as well. So we know the structure of really quite a lot of stuff that's in our address space, ideally all the things that are in our address space. Okay, so that's a kind of useful start. Is that enough of a demo? No one seems that convinced. Any questions?
Performance overhead.
Yeah, I have a slide about that. It's in another deck. I should have included it. Basically, having that information available for most programs will cost you less than 5% of runtime. And actually, that is almost all the overhead is quite easily optimizable away. I just haven't done it yet. So it's not actually changing very much at runtime. All it's doing, the only thing that's different, apart from a bit of startup, initialize some stuff. Sorry, I meant to say time. Yeah, memory is a bit more fuzzy. So I'll tell you about the time thing for now. You can ask me about memory in a sec. The only thing it's doing differently is when you do a malloc, it does a tiny bit of extra work to keep an index of what has been mallocked, sort of, which really is just kind of setting a bit in a bitmap sort of thing and saying here's the start of a malloc chunk. And also adding a bit of, it has one word, getting onto a memory question, one word for each malloc chunk. Just so I need to remember basically where that chunk came from and what its type is. So not too much overhead there. The metadata that we generate statically, that just gets DL open. It's harder to quantify what that overhead is because a lot of it's kind of demand paged and it depends basically how much you use it. But if you don't use this, the baseline overhead is very low. There are some exceptions. If you have your really funky allocators, if you have a program with its own funky allocators, it's kind of up to you to implement that meta-level API. I have some sort of naive implementations that will get you going, but they're pretty slow. So if you have something with its custom allocator like a custom allocator that is not malloc-like, then suddenly you need a slightly more, either a more custom implementation or more naive general implementation. And then you pay a bit more because you're doing more work at each allocation. But for most programs that are just using standard allocators, the overhead is pretty low.
Can I follow up? Most of these kind of Unix and C are very related, right? So do you envision, say you were designing a new systems programming language, would you design it differently so it could support this sort of introspection from the start? Or, let's say, that's kind of the programming language side of it, the hardware, like Cherry, which you're familiar with, can say this is a pointer at runtime, and the hardware can tell you that, and you might not need the source level information at that point.
There's a strong case for tagged memory. I think that if we could redesign hardware from scratch, we would have something like that. And yeah, Cherry is sort of uses a particular case of tagged memory. I don't see introspection as a language level feature. I see it as something you can fit onto the side of potentially any language. And in fact, if you look at the retrospectives on how Java does reflection, there's a very influential paper by Gillard Brack and Dave Unger from OOPS.04, I think, about mirrors. And they said, yeah, we built in too much stuff into the core language. Like the core Java reflection is not very well designed. It's very inflexible. We should actually have separated it out and made it more optional. So that's it's not just me who thinks that reflection is not, strictly speaking, something that needs to go into a language core, yeah. I think Fabio's got one over there. Oh, sorry.
Hi. So what you've shown us in this demo is basically introspection.
Yes.
So I was wondering if there was some more interesting capabilities and some more interactions that you can do with this live code.
Yeah.
And there's also something that you say in your abstract about linking NGC amount into the same problem. So
Yes.
I was wondering.
You've read my abstract. Very good. So. Right, let me get on. Basically, I can answer that by going further with the talk. So I don't know whose time this is coming out of at this point, but it doesn't seem to matter. So, focus. Okay. Right, sorry, went too far. So I haven't really talked about the liveness thing at all yet. We're sort of seeing some of the foundations. So what would be really nice to do is be able to actually update a running program, right? That's sort of what I'm working towards. The reason I asked for a chess timer talk is that I was hit by we've all heard the mythical man month, right? I got hit by this thing called the mythical academic summer, which is I put loads of things on my list of things. I definitely have time to do that in the summer. And then I got strictly less done overall than I would have done by not adding all those things. So here are the things that I think we need to do in order to make our Unix processes live updatable. It doesn't work yet. I was hoping to have a little demo that was at least proof of concept. I've only got some bits and bobs, but I can show you some bits and bobs. So the ones I've highlighted in bold are things I have something to say about today, if we have time. So the first one is obviously, we want the source to be in the program somehow. That's files again. See, I use files. We use files. We have something about the compiler being available. I'm just going to assume that we can run the compiler somehow, whichever compiler we need. I'm not going to worry about editors. I'm going to assume we know about dependencies enough to decide what needs recompiling or what needs updating, given a particular change. We're going to augment our runtime, and we're going to do something about pointer traversal and pointer sort of relinking and replacing. So this is coming on to the linking stroke garbage collection, the kind of the same underlying infrastructure. The punchline is that they're both about knowing where the pointers are, right? If you know where the pointers are, you can link your code, so you can reinsert things and splice things together and relay out things. That's exactly what a modern garbage collector needs. So let's see how far we can get. So if you look at the literature on dynamic update in a sort of C/Unix environment, these are two pieces of work that are really cool, right? The first one is Kitsune from University of Maryland, so Mike Hicks, Ted Smith, some other people. Really nice, really neat system. And the bottom one is Upstairs, so it's from Christis Makris, PhD work from Arizona State about 10 years ago. They're both really cool systems, but they both have this sort of recurring problem, which is that they basically don't understand enough about memory. So this is a snippet, the top bit is a snippet from the Kitsune paper. It says, well, we've got this limitation that we don't really understand custom memory allocators, And also, we're not very good if you give us if the program has pointers to the interior of objects. We can't really handle that because we want to build a new heap by basically calling malloc and free, whatever. So we need the base pointer. If you've got a program that's storing lots of interior pointers, then we're going to have to work around that somehow. So that's sort of limitation of one system. And then the other is upstairs, which is really cool because it basically takes your stack. It basically says, well, you want to update a program and, oh, you're updating a function on the stack. Well, it's okay. I can just produce a whole new stack, basically rewrite the stack. Here's your new stack that's like it should be, but, you know, with the updated stuff. So that's quite a clever, quite a sort of powerful facility. But it says, oh, well, we've got this problem with void pointers. Like, we don't know what's on the end of a void pointer. So, you know, if we want to update the state of your program, then, well, we don't have a good solution to that at the moment. So, funnily enough, I've been working on just such a thing, right? So this is all a very good fit. And one of the things about liballocs to come back to the why question, is that, well, it doesn't have a single headline use case. It has a sort of long tail it comes in handy again and again and again for realizing a whole bunch of things. I have a huge list of those on the README if you look at my GitHub page. I won't go into it now. Also, the Apple people, this is the LLDB projects page on the so you might say debuggers, some debuggers can do this, right? They can fix the code and you can continue executing. And you read the fix and continue sort of project suggestion for LLDB and they say, oh, well, this has been done before, but the tricky part is making sure the user can't do any of the updates they really want to do. Like, oh, they want to change the size of this object. No, tell them they can't do it. Or, you know, you want to update some function that's on the stack. No, just tell them they can't do it. Tell them that's impossible. So if we have an extended Unix, one that actually, they've sort of come to this conclusion by treating Unix as immutable, saying, well, we don't have the infrastructure for doing those things. So let's just say, let's not do them, or let's just work around them. But we could evolve Unix so that it can do it, right? How am I doing for time? Whose time am I on? Okay, it's about even. Good, okay. So, any questions before I go on to talk about source files? This is the easy part. This is quite easy. This is maybe a bit boring. I'll try and do it quickly. So we can think about an executable on disk as an image of memory, right? It's saying this is what your memory should contain when the program starts. And if it's a dynamically linked program, say it's only a partial image, right? Because there's some stuff that's not in this binary, it's in some other binary, but you know, it's part of the image. And there's a kind of weird thing that this is limited to memory, right? Because a very big part of the Unix execution model is you've got a file system. And it kind of makes sense to me that you would want a binary to be able to say, oh, in my initial image, I want it to be that there's this content at this place in the file system under this file name. That's quite a natural thing to me. It's not always what you want. Some files are there for communicating. They're not. Some files are there for sort of private purposes. So it's not so sometimes you want the file system to be an external shared space, but sometimes you want it to be sort of something that's tightly coupled to my program. And actually, source code is a great example of that, right? We have some source code that's very particular to my currently running program. And in fact, if you look at the debugging information, this is kind of a weird thing. You compile a little program and you inspect the debugging information that comes out. The debugging information records stuff about the build host, right? It gives you paths saying, oh, well, when I compiled this true.c, just a tiny little program, it was compiled in some directory, but that's on the build program. And when we start shipping binaries around, then that connection is broken. So this is why you download the debug symbols for some package on your Linux system. They will just have some random path that was whatever the path was on the build machine, right? So those files actually, they belong with the binary. Why don't we bundle the source code into the binary? Then we can actually start doing cool live things with it. So wouldn't it be nice if our program actually opened this test.c at the path that the debug information says that's where the source code is, that it actually saw the source code. So this is one thing I have actually done. So I've prototyped this really simple, it's not very exciting, but it lets you bundle a file into an ELF file, and then that file is available at runtime. What I haven't yet done, but is not too difficult, is to intercept the system calls for opening and reading stuff, so that if you try and open that file, you'll see the content that was bundled in your file. Currently, this program, it does print its own source code, so I don't think it counts as a quine, but still, it reads its own source code through the file system because it knows that that code is bundled into the binary that the program itself is made from. Okay, so we can kind of do this what I call a source in situ, having the source code available when our program is running. It's not too difficult. We do need to hook the system calls that access the file system so that they can access those paths by accessing the binary itself. So that's something that, again, liballocs is already doing some stuff of that kind. It's already hooking mmap. We just need to hook a few more things and plumb them together. Obviously, file system APIs are a bit subtle in some places, so it's not trivial, but it's also pretty obviously achievable. There's an interesting question about whether this is a design, how this affects the Unix level design, right? Because if you start bundling files into programs, it gets a bit difficult to see exactly what's going on. The file system is already a per process namespace. This is kind of taking it a bit further. So there's some interesting questions about when it's appropriate to use this versus not. Okay, I've only got 3 minutes left, so someone better ask me another question. Yes.
So I'm wondering, you said you're inspired by Smalltalk and you're trying to make Unix more live. Why not try and run Smalltalk instead of your operating system?
Well, it's almost a philosophical question, right? When does it count as the operating system? I mean, the main reason is what I gave at the beginning, right? That the world is not written in Smalltalk. Sad times. It should be, maybe. I mean, the other thing, I have other talks and papers about the philosophical differences between Unix and Smalltalk. I think Unix won because it's very pluralist, right? You can do a lot of different things with Unix, it just doesn't care. It just lets you, so for better or worse, that's allowed it to sort of stay simple to implement, be very widespread, and so on. So it's a big issue, but I'm going to stick with my first answer saying the world is written in Unix whether we like it or not. Yeah. Any more? Shall I try and use one over there?
Hello, me again.
Oh,
optimized code. Optimizing compilers can delete variables, move them around, inline functions. How are you going to planning? What are your thoughts on that?
Well, so there's good news and bad news. Okay. The good news is I'm going to take you way back. Oh, it's actually the demo I need to show you. If I still got it on my terminal. So when I showed you the output of this demo, I said that the stack frame is understood as a struct, right? So what that struct is generated by looking at the debug information that comes out of the compiler, doing some quite hairy post-processing to basically figure out which bits are staying the same as the program counter moves through the function. Basically because the compiler is outputting very, very detailed information. It's also incomplete information, which is the annoying thing, but it's very, very detailed information about where each local variable is living, and so there's lots of optimization. So it's in register here, then it moves to this particular slot in the stack, and then it's a different register, and then it's split between this register and that register. So the information is already very detailed, and that's what allows you to debug optimized code. We all know that debugging optimized code is fraught with things where the information just kind of runs out, because the compiler the transformations done by the compiler are not matched with equally precise descriptions of what it's done. There's another slight quirk, which is that sometimes there's not preserved a simulation between the source program and the running binary. That's not so much of an issue here. It's a bit of an issue, but knowing where all the pointers are does require us to have complete information out of the compiler, which currently they don't quite give us. They sort of aspire to maybe ideally giving it to us and then kind of give up at some places. So fixing that is a research problem that basically says, can we make it easier to write compiler passes in ways that preserve debugging information? I have a bit of work on this already. If anyone is interested in talking to me about doing more and better versions of that, that's something I'm super interested in doing. And it affects both the debugging experience and the ability to do crazy things like this. Janis, did you have a question? No.
Not entirely a question, but what you're basically saying is that we have managed languages and we have unmanaged languages at the very low level, at the Unix level. So let's bring the facilities from managed languages to the Unix level. But this is not cost-free. So you will have an overhead and you will have a compliance overhead because you want people to use you want languages to use your API to declare types, for instance.
Well, no, I don't. I just want them to use standard debug information. There's no APIs involved with getting that type information.
Well, if I don't want to compile my program for debugging at all, I mean, if I deploy, I'm not debugging. So the real question is, why would I want to do this? Why not have C as a JVM language if I want this facility? Or why would I care to bring that to languages that are explicitly trying to be close to the metal? And do you also see some way to perhaps do this heuristically so you don't require any cooperation and maybe you can get it to be overhead free? Because that might begin to be interesting, I think.
So like I said, I think that the baseline overhead of running this stuff for, you compile a pile of C code, you run it like this, I think that can be brought down to something negligible, and I'm very interested in doing the follow-up work that will achieve that. There's a lot of other stuff mixed up in your question. I won't be able to do justice to all of it, but you made a sort of dichotomy between languages that are trying to be close to the metal and higher-level managed languages. I fundamentally don't believe that dichotomy, partly because a lot of C code is actually not particularly low-level in its essence, right? And equally, current ways of realizing managed languages are basically doing this layering thing that I said at the beginning, right? And that causes, basically we have a very fragmented, very splitted infrastructure where everything is duplicated. Like, we basically have silos. Everything grows in these silos. I don't believe that's a necessary structure, and I think it causes a long tail of hidden costs to the development experience, right? Because we have to manage the gaps between these silos, we have to bridge these constantly. There's sort of a lot of hidden work in doing that as a sort of day-to-day development activity. So a lot of cost from fragmentation, right? Because the same thing gets implemented for Java and for C and for yada, yada, yada. So that's the sort of core of the structural problem that I'm attacking here. It's a lot of work. Does that help at all? A little bit. Okay, maybe we can talk later. How are we doing for time? Okay, we've got 4-ish minutes left. Any more? Well, basically it's a toss-up as to who has the floor now, because we're both on not very many minutes left. I'm just going to quickly try and finish a bit of my story about liveness, if that's all right, and then you can quiz me a little bit. So we've done the images thing, we've done the files thing, taking over user space. So I mentioned earlier that I do this LD preload thing. LD preload is a horrible hack. It just lets you get your code in there. But there's a thing that's actually a reasonably principled way of taking over user space, which is to write your own dynamic linker. If I had more time, I'll tell you about how to do that. Or not even just write your own, right, but just make an extended version of the current one. Turns out that's really quite easy to do. And I have some little sort of build scripts and helpers that will basically help you build a dynamic linker that is like the one on your system, but has your code in it that runs right at the beginning, so you can get control. And once you have control of the dynamic linker, you can do whatever you want, right? You can control the whole of user space. There's a little quiz question that I was going to ask, but I've given away the answer now, which is, what is the first user space code to run on a Linux system? You think about booting a system, you've got the kernel, and then at some point you have user space, and no one people put init, which is almost right, but init is dynamically linked. So the first thing that runs is actually the startup instructions in a dynamic linker. So if you can get in there, you're really in really, really early. So building your own dynamic linker is kind of interesting, not too difficult. And then it comes back to knowing where the pointers are, right? Because what's the first thing a dynamic linker has to do? Well, it doesn't know where it's been loaded in memory. It's a binary, it's been loaded somewhere, and if you load any other shared library, it's the dynamic linker's job to fix up that library so that any pointers that need to be rewritten are rewritten. The dynamic linker is a shared library, but it has no other dynamic linker to relocate itself. So the first thing it does is this incredibly hairy code to basically walk through, it's at the bottom of the slide here, basically walk through its own relocation table and fix itself up. And that code is written in C, but it's not normal C, because you can't do things that you could do in normal C. Like, you can't access a global variable depending on the addressing modes available. You can do PC relative things, but you can't do absolute addresses, because you don't know what the absolute address of anything is yet. Until you fix it up, everything's pointing to the wrong place. So that's kind of a hilarious bit of code to look at if you're ever in the mood for something really grungy. But the interesting thing is that you can ask a linker to tell me, any binary that it generates, you can just ask it to tell me where are the pointers. You basically tell it to emit relocations. So instead of just patching up the stuff, applying the fix-up, making the pointers point to places, you can actually make it leave the records in there that say, oh, tell me what you patched up. So it really gives you a kind of quite complete set of pointer information for that static stuff. Right? So we've done the static stuff. We've got to worry about other pointers in heap and stack, but we've already covered that, I think. We've got some type information for the heap. I didn't tell you how that worked, by the way. You can ask me that. And we've got some information for the stack as well, but as I mentioned, it's not complete because of what compilers currently do, but I'm working on that. Okay, so I didn't quite get to showing you a demoable full live system, which doesn't exist yet, but I more or less got to the end of what I wanted to say. How many minutes do we have? 1:36 of audience time left. Okay, so it's your time to ask me questions that will fit in 1 minute 36.
Live live programmable Unix sounds awesome. What's the biggest obstacle?
In practice, it's the compiler thing I mentioned, right? You look at what liballoc knows about the stack, and it will say, I know this bit, and then there's a hole. It's like, I don't know what's on the stack there. So you have to fall back to the traditional, currently you have to fall back to traditional sort of conservative techniques of saying, well, what if I suppose it could be a pointer? Does it look like a sane pointer? That's definitely not satisfactory. So fixing the compilers so that they can either scale back the optimizations a little bit so they can actually give me a complete description, or fix the passes so that they do generate full information about the code they generate. Either one of those would be a workable fix. That's quite a lot of work, and that's the main practical obstacle at the moment, I would say.
This is a cheat because it's not a question. I think I heard someone mutter earlier, I must come and visit this Kent place. You are all welcome to come and visit our very wonderful programming languages group in Canterbury. It's only 55 minutes on the train from St Pancras.
Yes, please do. It's a wonderful place. We have good people, and me. Thank you, thank you. Punchline. Saying about there being a long tail of use cases of this thing. So people end up implementing it badly, kind of half of it badly. I'm trying to do the full thing semi-well. Yeah.
I could raise mild objections again. I mean, part of my problem is if you see the pains that C++ takes to avoid RTTI overhead when it can. I mean, it just seems like you start from the premise that what if these languages were willing to give me this information when these languages are explicitly designed to not do that? They are the last frontier that has decided to not give you that information that you want. So that's what confuses me. And when you say C code is not necessarily low level, new C code, anyone who decides to write new C code probably wants something low level. Why are we only interested in new C code? The very beginning of my talk was explicitly saying, we don't just care about new stuff, right? I care about there being a huge mass of C code that on any commodity software distribution has been written often decades ago and is still there, still causes problems, right? We still have to maintain it, debug it, it still has security issues, all the rest of it. So I definitely, I mean, this argument is, I appreciate you raising it, but I believe it's fundamentally wrong, right? It's not just about new code. And, okay, what else did you say? You have to remind me, sorry. So I said, I don't think the overhead would be acceptable just because of the C++ RTTI. So there is a culture, if people have numbers in their mind, they say, 3% is okay, and 5% is not great, and 10% is bad. I think that is just, I mean, I don't know where those numbers come from. If you say, you know, what is an acceptable slowdown for production, whatever. Again, I could go on many rants about this, but basically I think there are huge benefits. Yeah, how much does it cost to fix security? If people say, I don't want to have bounds checking in my C code because that would cost me X% of runtime, and that would be bad. But how much do people spend on this huge apparatus for mitigating these, you know, patching software, mitigating security problems, the cost of actually exploits, whatever. So this is a simple, you know, example of what are the real costs of this stuff. No one really knows what the real costs are. People just have numbers in their head saying, oh, this much is enough, this much is too much. It's a cultural thing, and I'm not necessarily going to change culture overnight, but I've got to build a thing that provides an option, provides a new way of doing things. It might be useful to someone. I have no objection to the philosophy, but what I'm trying to influence you towards doing something heuristic that will get most of the benefit, like all the smart allocators that Emery Berger has been building to give you some of those either guarantees or checking of good properties without touching the application. And you require recompilation. And I'm saying, instead of requiring recompilation, why don't you just LD preload your stuff and then try to guess types, try to do interesting things heuristically and get much of the benefit without having this burden of adoption.
So getting types actually doesn't require recompilation. That's just a factual point. I have my compiler wrapper because it's a convenience and because, well, for incidental reasons, let's say. So getting the type information doesn't require recompilation. Obviously, doing extra instrumentation to like do checking or whatever, yes, that does, because that's changing the code. You could imagine doing that at a binary level. So yeah, I'm with you. I was worried you were saying that my approach was invalidated by your concerns, and I don't believe it is. Okay, thanks.
All right, we are out of time. So I guess any further discussion will have to be offline. The next talk is going to be great.